Part of the lesson, we're going to be taking a look at a few postulates in geometry. The question is, what is a postulate? Well, a postulate is a statement that is accepted as true without proof. We're going to run into a lot of different postulates this year. Now, just because I say it's accepted as true without proof doesn't mean that it's a weak statement or anything. What it means is that it's so self-evidently true that it doesn't need to have proof for us to accept it. Or it might be something that we need as a building block to explain a more complicated topic. Okay, that's what a postulate is, though. Something that is accepted as true without proof. Usually it's something that's self-evidently true. And we're going to be dealing with a postulate called the ruler postulate. Now, this is a postulate specific to modern geometry. This is not one that Euclid would have dealt with, because remember, Euclid didn't really do any measurement with rulers. And this is a postulate all about measuring things using rulers. So it actually, this is the postulate that's like the foundation on which a ruler works. Okay, so let's take a look at what this is. The postulate states that the points on a line can be paired in a one-to-one correspondence with the real numbers. So the points on a line, like on a ruler, can be paired in a one-to-one correspondence with the real numbers such that any two given points can have coordinates 0 and 1. Those 2 points, by the way, are going to have a certain distance between them, and they're going to form the basis on which all of the scale of the ruler is built. So whatever distance is between 0 and 1, that's going to be the same distance between 1 and 2, 2 and 3, -1 and 0. Okay, so that's important. And then secondly, the distance between 2 points is the absolute value of the difference of their coordinates. What in the world does that mean? Well, this one is best understood if we look at a real world example. So first of all, I use this word distance. Let's define the word distance here. We defined the word length before. Let's define the word distance. It's the measure of the segment connecting 2 points. Length and distance are very similar terms. I would say that distance is more specific because we're dealing with segments and points. Length, remember, was just the extent to which something extends in one dimension. So that was a lot more vague language. Distance is a little more specific to what we're dealing with. Segment and points, endpoints. All right, now let's take a look at a segment with some endpoints. We'll take a look at this one. Here I have segment AB, okay? And I'm going to note that AB has a distance of 4. How do I know that AB, though, has a distance of 4? Well, if I'm stating the distance of AB, that means that I must have measured it according to some measurement instrument. And my measurement instrument is basically just a number line. My measuring instrument could start at 0 and go to some positive integer. It could even, if I wanted to, now most rulers don't do this, but I could start a ruler at a negative integer and go to a positive integer. One of the things that the first part of the postulate states is that it doesn't really matter which coordinates have 0 and 1. And part of that means that I could make a coordinate 0 that forces some other coordinates to be negative. And that's exactly what I did here with this number line. Okay, now I notice that A is at -3 and B is at 1. So how do I measure the distance from point A to point B? Or I guess the length of that segment? Well, the way to do it is just, it says the distance between 2 points is the absolute value of the difference of their coordinates. One of their coordinates is 1, one of those coordinates is -3. If I take the difference of those coordinates, 1 minus -3, so point B is at 1, point A is at -3, I'm going to find the difference of those coordinates, 1 minus -3. That's the same as 1 plus 3. And the absolute value of that, 1 plus 3 is 4. The absolute value of 4 is 4. I could also do this the other way, though. I could assign the other coordinate first. -3 minus 1. Well, -3 minus 1 is -4. Okay, that's the difference between coordinates 2. The absolute value of -4 is 4. Okay, so regardless of which coordinate I use first or which one I use second, as long as I take the absolute value, I will get the distance between the 2 points. All right, moving on. Let's take a look at another postulate. This is known as the segment addition postulate. if B is a point between points A and C, and this is going to be on a line segment, okay? So if B is between A and C, then AB plus BC equals AC. Now, wait a minute here. Wait a minute. Why don't I have line segment lines over AB and BC and AC? Notice that it just lists the 2 points without putting a line segment notation above it. The reason for that is because now we're dealing with a distance. And whenever I'm dealing with a distance between points, an actual distance that has a number assigned to it, I can just note the names of the points without putting the line segment in anymore. For example, up above where I had AB measured out as 4, if I wanted to write that, I could do it like this. The measure of AB without a segment notation above it is 4. Okay, so whenever I'm dealing with distances that have been measured, I can drop the line segment notation and just use the points. AB equals 4. Now, we're going to consider that AB in just a moment here. If B is a point between A and C, then AB plus BC equals AC. If I have a point in between 2 other points on a line segment, if I add the 2 smaller segments, I get the bigger segment. That's what's going on here. So let me go ahead and show a point C up here. Now, if what I'm saying here is that if I add together AB and BC, I should get the full distance AC. Now, before I do that, let's just verify that BC has a distance of 2. So looking at this, if I use my ruler postulate, I'm going to do 1 minus 3. I subtract the difference between 2 coordinates. 1 minus 3 is negative 2. Absolute value of that is 2. Alternatively, I could do 3 minus 1, which is just 2, and then the absolute value of that is still 2. So I've confirmed that BC is 2. Hey, would you be able to do AC right away? A is negative 3. C is 3. So if I did negative 3 minus 3, that gives me negative 6. The absolute value of that is 6. Or 3 minus negative 3 is 3 plus 3, 6. Let's confirm using the segment addition postulate that the length, the distance between A and C is actually 6. So I know that AB is 4. I know that BC is 2. And according to the segment addition postulate, AC should equal AB plus BC. In other words, AC should equal 4 plus 2. And 4 plus 2 equals 6. So this confirms the segment addition postulate. And I didn't need to prove the segment addition postulate. It's a postulate. We accept it as true without proof. But it's self-evidently true anyway. And I can do these little proofs like this that show that it is true. All right, now let's finish this up. We're going to talk about the term midpoint. A midpoint is a point between, notice in the segment addition postulate, we found a point B between A and C. A midpoint is like that. It's a point between 2 points on a segment, but it divides the segment into 2 equal parts. So it's a special in-between point, a special in-between point that perfectly divides a segment into 2 equal parts. Here I have the segment AB and the midpoint of AB right in the middle, so it divides AB into 2 equal parts. And if it divides AB into 2 equal parts, I can state that if M is the midpoint of AB, segment AB, okay, notice that's segment notation, then the measure of AM, it's not segment notation, so I'm talking about a distance there. The distance AM is equal to the distance MB. Hey, let's just talk for a moment about length and distance versus congruency, which we talked about in the previous video. Now, distances can be equal. AM equals MB. Notice I didn't say that AM is congruent to MB. And the reason for that is when I talk about distances, numbers, values that we assign to things, values can be equal to one another. So it's important for you to realize distances or lengths can be equal to one another. Segments, though, the actual figures themselves that have shape, we talked about how line segments kind of all have the same shape and distance, segments can be congruent to one another. So I could say that AM, the segment, as long as I put segment notation over the top, if I put a line segment over here, I could say that AM, the segment, is congruent to MB, the segment. Okay, if I had segment notation, then I could put a congruency symbol in between here. That's the equal sign with the little squiggle over the top. However, if I'm just talking like here, I am talking just about AM, the measure, and MB, the measure, I would never say those are congruent because measured values are equal. So I'm going to use an equal sign instead of a congruency sign. I just want to make that point because that's going to come up in the homework from time to time. You need to be able to articulate that segments can be congruent because we're talking about the figures. Figures can be congruent. So therefore segments, which are figures, can be congruent. But measured values can't be congruent. They don't have shape. Measured values can be equal to one another. And that's the end of lesson 2, part 2. Next, we're going to work some example problems.